So welcome back. And this is actually our second last lecture. And what you will see from the slides this week is that there is probably much more material than we will have time to cover. And the material about the adversarial networks is probably something which we will start scratching the surface of today. But then we will conclude that in the last lecture, which is not next week, because next Thursday is a public holiday in Norway. So we will have a final lecture, which will be on May 21. And then we will also do a summary. So probably I will get into GANs, but I will probably not be able to wrap it fully up. And that will be the last topic. I was thinking of putting in something about normalizing flows, but I will probably not get the time to do that. I had forgotten actually that next week was a public holiday. So sorry for that. And what I wanted to bring up now is a quick repetition about variational autoencoders, and then go back again and look at a little bit more the mathematics and details of diffusion models and what they're actually doing. So keep in mind that diffusion models are perhaps the most popular models nowadays, but they are extremely heavy to train. So you can actually run a training for many, many hours on GPUs. So they are the codes which I have, unless you have access to GPUs, they're going to be extremely slow. Actually, the code I had took close to 20 hours to run properly. Okay, so I wanted to give you a quick overview. So we are going to look at the basic elements of what is called a variational diffusion model, which is one of the more standard ones. And actually, these diffusion models are very, very popular, and they're inspired by, for those of you familiar with physics and the process of diffusion and non-equilibrium thermodynamics, it's very much based on that. So they defined a Markov chain of diffusion steps that slowly adds random noise to the data. And then they learned to reverse the diffusion process so that you can reconstruct the desired data sample from the noise. And unlike the variational autoencoders, the diffusion models are typically learned with a fixed procedure. We will come back to that. The other thing is that if you think back to variational autoencoders with a latent space, which is meant to represent some effective degrees of freedom, the hidden spaces or the hidden degrees of freedom for diffusion models are exactly the same as the original data space. So there is no kind of I'll say saving in dimensionalities. And we are not looking after a way to find some kind of effective degrees of freedom. So it's diffusion models are actually very prominent in generating high quality images, video and sound. And they're obviously named for their similarity to the diffusion process in physics. And you generate typically new data by reversing a diffusion process. So you're undoing information loss due to noise. And the main idea is to add random noise to data, then undo the process to recover the original data distribution. And then you train a probability distribution through that. So when you've trained this probability distribution, then you do have the probability which you can use to generate new images. And if you go to softwares like, so some of you may have used the DAL-E, which was a very popular application, and also open source softwares like Stable Diffusions. These are actually models which create realistic images from input. And they are extremely popular. So what we are going to do now is to, after some brief repetition of, that was not the one I wanted to show, we are going to have a quick repetition of many of these models which we have encountered. And so the VIEs, they use this lower bound optimization. And there is typically one pass from the decoder, whereas the diffusion models uses the same, but then it uses T denoiser calls, as we will see more in detail now. And the GANs, on the other hand, they actually don't. So variational autoencoders and diffusion models, they generate a probability distribution. GANs do not. They actually implicitly generate a distribution for you. So if you're interested in a probability distribution, then variational autoencoders and diffusion models are actually much more popular. And diffusion models, they are hierarchical variational autoencoders with many, many latent levels. And then it has a fixed, so you don't learn that one. So the encoder is actually set by specific parameterizations, which often means a Gaussian distribution in a specific way. So it's actually fixed for us. And it's not like the variational autoencoder where we actually train the decoder. So as it says here in the slides, understanding the VIEs is actually normally the fastest route to understanding diffusion, as we also discussed last week when we had a repetition of the variational autoencoders. So let me quickly say a little bit about the variational autoencoders. And before we look at this slide, I simply wanted to bring back the whiteboard so that we can see a little bit the kind of general image and concepts which we have with a variational autoencoder compared with a diffusion model. So when we looked at the variational autoencoder, let me just do one thing here. Some paper. Just need to leave a little bit. Sorry for this. So if we look at the typical picture which you see when we have a variational autoencoder. So let me remind you of this one from last week and the week before. So you would have the data here that has a specific dimensionality. This is a data in. It could be an image which you want to use to train or sets of images. Then there is a decoder part, and there is a conditional probability which is trained. Normally this is actually trained by, again, a Gaussian, as we discussed last time. And you have now a probability of finding H. There are some parameters phi, and finding H given X. So get X is your input data. So this is a probability which is then trained. And this is the encoder part. Then we transfer this one into what we call the latent space. And this latent space now contains these degrees of freedom, which we label as H. And you can think of this as the hidden layers of a neural network, as an example. They play the same role. But in our case, this is a parallel to what we had with autoencoders, in the sense that these H's are going to represent some effective degrees of freedom, which we then can use to represent, for instance, the numbers from the MNIST data set. And in this case, we have a probability distribution, P of theta, and theta is one of the parameters which we are going to train. Now, this P of theta is used then to decode. So there is a decoder part. And then there is a new conditional probability which links the latent space. And normally this probability is assumed to be fixed. And this is given by a normal distribution with zero mean. So the latent part is actually fixed. And variational autoencoders are actually also called variational Bayesian networks, because it's a repeated usage of Bayes' theorem, which relates the probabilities. And in this particular case, we're interested in X given H. And then this is then used to produce the final probability. So the goal is for us to have a probability distribution P of theta of X. That's the final goal. And then we are going to produce new samples, which then will be given by this probability distribution. So when you have done this training, then you could actually make images of new horses, etc., etc. So essentially, this is the loop of a variational autoencoder. And the basic mathematical expressions which link these different terms is us having a probability, a final probability. So this P of theta of X is now a probability which is given by an integral over the latent degrees of freedom. And then we have the probability of having both X and H. Now, this quantity here is again given by the product rule. So that means that this can be rewritten as a D of H. And essentially what we are doing is variations of these type of calculations. So this P theta of X, we want to get rid of the latent degrees of freedom. So this will contain X given H multiplied with P theta of H. So this is the link between the latent space. So this is our latent space. It's often called a prior, following Bayes' theorem. So we would call this a prior. And then this is just a likelihood. And this is actually the decoder part. And these are the probability which are then trained. And the way we would typically train this is that we obviously end up with a different set of integrals, which are given by expectation values. And the P theta, which we actually end up having, is something which we then can describe in terms of expectation values. So let me just bring back the slide. So this was a very, very quick repetition of variational autoencoders. And when we now go to diffusion models, the difference in that case is actually us now taking into account many, many different latent steps. So you could now think of a diffusion model where you have an initial distribution and the initial data, which we label with an X0. Then this is now transferred to some H1, H2. So if the dimensionalities are different, you could think of these as latent degrees of freedom, where you then would couple, if you now just repeat what we had with variational autoencoders, you would then have a probability distribution for H1, which would have trainable parameters. And you see that this quickly becomes heavy if you want to train all parameters, because each one of these could have a set of parameters to be trained. And then you would link the next one, which would give you a Q of H2 given H1. And this would continue all the way till the final one here, where you'd have a Q of H of T minus 1 given an H of T here. Now, this is then used to reconstruct a probability, the final probability distribution, where you now would have an X of T minus 1 given X of T, H of T. And this continues all the way back here, where you now have a final distribution, which is given by P, and these have all parameters, which I'm suppressing in the notation here, where we would have X of 0 given an H of 1 here. Now, it's not normally done this way. So you will see that in the notation which we have in the slides, we are going to replace these H's because in a diffusion model, what we end up having, we have that the dimension of H1, H2 up to H of T is the same as the original data set X. So there is no effective reduction. And you see quickly now that if you're going to train different functions Q here, this is going to be pretty unwieldy. So in the beginning, we are going to set up the equation as if we are going to do that. But then we are going to replace them with fixed functions, which are then just set up so that they weakly depend on each other. And there is a recipe in the lecture notes, which we are going to discuss in more detail. Now, the final distribution is the one which we obviously are aiming at. So if we now think of these different steps which we have here. So what we are interested in is a probability. If you're looking at these diffusion models, we have a probability of x0 and given some h from 1 to t. And this is a probability which we then can single out in terms of all the small steps up to t. So we are going to have a probability for this latent space, h of t. This is going to contain parameters. So ph of t is normally fixed to be a specific probability. And if you think back to what we did with the variational autoencoders, this is normally given by a normal distribution with 0, mean, and variance 1. Because at a certain point, you have to choose a model for this. Because else, to train all these different steps is typically something which would be almost impossible to do. So then, what we have is now a set of products here, where now I'm singling out this h0 of h1. So that's the step. And then this is multiplied with all the other conditional probabilities up to t, and p theta, where we have theta, the ideal, which we actually are not going to use, of t. So we have all these subsequent probabilities which link us from this one till the final one, and where we have made an assumption for this specific probability. Then we have the decoder part. So you can think of this as the decoder part with 1 to t steps. And often t is on the order of 100 or more. And then you clearly see that this is going to be pretty heavy. So these are typical processes which are run on GPUs and parallelized and made as efficient as possible. So if you were to run this on your laptop without access to GPUs, it's going to be pretty slow. So the next thing which we need then is this guy here, which will also depend on some parameters, ideally. So this is an h from 1 to t, given the input x0. And this is again equal to a q of phi. And then I have h1 linking with x0. So this is the encoder part. And this is multiplied with all the other guys, which would go from t2 up to the final t. And then I had a q of phi of h of t, given h of t minus 1. So what we want to optimize is obviously the marginal probability. And we know that the marginal probability, if we now look at this chain of events, so we want to optimize, we optimize the marginal probability and this part here follows exactly the same steps which we had for variational autoencoders. And typically what we end up with then is to optimize the log of the probability. And you can see now that on this probability, I'm suppressing the variables theta and phi. So if you now look at these variables which we have here, so this is fixed, typically just a normal distribution with the 0 mean and variance 1. But then we have parameters here, and we have parameters here. So it looks like an almost impossible task. Now, in the equation which you will see here, I'm suppressing the dependence on these different variables, theta and phi. And this is a quantity which in principle is equal to log And we are now integrating away all the other degrees of freedom. So we have an x0, and then we have h1. So this is the latent space multiplied with d of h1 to t. So these are the latent degrees of freedom, which we are just integrating away, as we did with variational autoencoders. So just to remind you, in the VIE part, what we had then is a log of p, and now I'm putting theta of x0, which was simply given by log of p of x0 given h multiplied with p theta of h d of h. So in that case, we had only one such hidden layer. Now, the way you would optimize this problem, and this is where it gets pretty unwieldy and where we have to make some approximations. So I'm just going to set up the basic equations as they would appear if we insist on having all these parameters and probabilities to fit. So the basic equation we would have then would be to fit, this is the function we want to optimize. So we would have a p of x0, and then we have h1 to t. And then we have, and what I'm doing now is I'm just inserting 1. So I have h1 to t given x0. And then I have a dh1 to t. And this is just divided by 1. So I'm just putting in 1 here. So this is just a trick which I'm using of x0. And this is something which I can rewrite as log of an expectation value. So I would set up this as a log of an expectation value where I have a q of phi, and I'm suppressing all this other notation here just for simplicity. So we have a probability, so we are drawing these random variables, h, using this probability. So we calculate an expectation value of the ratio between p of x0 of h1 to t divided by q of phi, and reminding ourselves of the Kullback-Leibler divergence, which we discussed last week. This is something which we can rewrite in terms of that. Actually, we are going to end up with something like 3 terms, which we're going to set up pretty soon. And there is something, and this Jensen is not a relative of mine. This is called Jensen's inequality in statistics, when you have log outside. So if you use that one, Jensen's inequality, the function we can then optimize is actually the expectation value of the log of these probabilities. And then we have log. So the proof for this one is something you can find in basically most textbooks in statistics, advanced statistics. And divided by q of phi of x1 to, h1 to t. Let me just rewrite it so it looks a little bit cleaner. So I have h1 to t given x0. And this is the quantity which we discussed last time as well in connection with variational autoencoders. So the trick which you see here is basically the same which we had then. The thing which complicates life now is actually that this probability distribution is actually pretty difficult to set up. And the same with that one, because if we now insist on this picture which we have here, what this becomes, when I now plug in all these different steps, the decoder and encoder steps for every single step here. So this process which you see here is actually based on the physical process of diffusion. And if I do that, then this equation here gets pretty ugly, because we are going to get something which now looks like this. So this is E, the expectation value, over Q of phi, Let me try to set it up properly. So I'm going to have a log, and I will have P of H of T, which is normally fixed, as we had for the decoder, the prior, it's normally called the prior. But then I have a P of theta, and I have X0 to H1. And then I have the product of all these other guys, T equal to 2 up to T of P theta. And then I have HT minus 1 of H of T. So that's one of the terms. And we have to divide that one with Q of phi of H1 X0 multiplied with new trainable distributions with parameters of T. And then we have a Q of phi of H of T of H of T minus 1. And this doesn't look very nice, actually. So how can we do? How can we actually solve this type of problem? So one of the things then is actually to replace and keep in mind that the H's are fixed. So the HI have same dim as X0. So what we are going to do now is simply to replace this one, because there's no point in calling this for hidden layers. The whole thing with a hidden layer or these hidden variables, latent variables, is that they are meant to express a reduced dimensionality and incorporate some effective degrees of freedom. So what we are going to do now is that we let all the H's simply go over to X of I. And the type of model which we are going to look at is something which is going to be called a variational diffusion model. So let me just bring up some slides again, because there are some words which I just wanted to bring up, and you have access to these in the PDF, where we have listed all the PDFs, but let me just bring up these slides here. And so there is an additional material where I actually put in some more words on diffusion models. So let's just go through these, and then we go back to the slides, no, to the whiteboard. So as I said, they are actually inspired by non-equilibrium thermodynamics. They actually learned with a typical fixed procedure. And the latent variable has high dimensionality, the same as the original data. So this is different. And as I said, so what we are doing now is we are going to progressively add some noise to our data set. And then we are going to learn to reverse this process to generate high quality data. So the central concept here is actually gradually degrading data quality only to reconstruct it so its original form or transform it into something new. And there are tons of applications here of these type of models. So historically, these probabilistic models, they typically suffer from a trade-off between two conflicting objectives. One, you want to have something which is analytically evaluated and easily to fit to data. So Gaussian is typically one of these. However, if you take these simpler models, which often give you analytical equations. So if you think of Bayes' theorem, and you have a prior which is given by uniform distribution, and you have which is basically a constant, and you multiply that with a likelihood which is a Gaussian, then your final probability distribution is a new Gaussian multiplied with a constant. So, and there you have nice analytical structures which you can exploit. However, in general, the data which you want to describe has a much more complex structure. And if you go back to Boltzmann machines, which we discussed earlier, then the typical problem is actually that computing C is generally intractable. So diffusion models, they are extremely flexible in model structure. They can give an exact sampling, it takes an easy multiplication, and there's a cheap evaluation of these log likelihoods and individual state probabilities. The only problem is that when you have many such steps T, this becomes heavy to train. And you will see that if you try to run the codes which I put up. So it uses basically a Markov chain to gradually convert one distribution into another one. And this is typically an idea which is taken from non-equilibrium statistical physics. So you build a generative Markov chain that converts a simple known distribution into a target data distribution via diffusion process. And since each step has an analytically evaluable probability, the full chain can also be analytically evaluated. So these are some of the basic things. So the learning then involves estimating small perturbations through a diffusion process. And estimating small analytically tractable perturbation is more tractable than describing the full distribution. Since a diffusion process exists for any smooth target distribution, this method can capture data distribution of arbitrary form. So they have two steps. One is the forward process. And if you think of this step where we just go from x0 to the last hidden layer, and then we reverse the process where we methodologically reverse the forward diffusion to recover clean data. So before diffusion process begins, you should try to do some data cleaning. This is pretty common with everything you do. There is no kind of difference here compared to any other machine learning method you use, whether you're using simple linear regression, logistic regression, or advanced deep learning methods. We try to remove outliers, we scale features, increase data set diversity, we do standardization, achieve normal data distribution. This is often important for noisy image in data. And then if you have different data types, they may require specific pre-processing steps. So when you have done the data processing, which is actually very important, that normally ensures that you have better training data. And it can often give a much more, a better trained model. So the kind of derivations which I've been using, if you go to this article here by Calvin Luo, this is basically something which I followed in the lecture notes here. So I wanted to describe to you now so this is actually what I put up on the whiteboard. And this is the more heavy part, which we are actually not going to use. So you can see I used X0 on my whiteboard. Here I use X. So this is essentially the Markovian variational autoencoder. So what I showed you on the whiteboard is normally mentioned as a Markovian variational autoencoder. And then we optimize this quantity here. And when we set everything in, we end up with having something like this, and which is very heavy to train. So what we are going to look at now is something which is called a variational diffusion model, which is one of the most standard approaches to diffusion model. And before we do that, let me quickly remind you of in the slides which we have for this specific week. So this is just an additional set of slides. So if we now look at the equation which we ended up for a variational autoencoder, we ended up with this equation here. This is the one we want to optimize. And this is something which then, if this is our loss function, so the loss function is actually this one, and it depends on the parameters theta and phi. Now, this function phi here, as you may remember from last time, is actually given in terms of a Gaussian with a mean value, which is then given by a trainable parameter. So this mean value depends on phi. But the probability distribution is fixed for the decoder. So it's pretty common to use a Gaussian decoder for variational autoencoders. And there is a prior for the latent space, which is just as I mentioned earlier, just a plain and normal distribution. And this H then is given in terms of this mean value plus some variation and multiplied with a noise which is normal distributed. And if I use that one, then this term here, which is called a regularization term, ends up with a closed form expression, which is easy to evaluate. But then we need to evaluate this one, the reconstruction integral, and that's normally evaluated by some standard calculations of an expectation value using some Monte Carlo sampling. So this is the basic step with a variational autoencoder. So they are powerful, and the equation which we have, this is called the elbow gap here, where we have L, the cost function, plus this one, because the Kullback-Leibler divergence is a quantity which is larger or equal than 0. So this quantity can be larger than L. So it's always a positive definite function. So it is a convex optimization problem or maximization problem. And the problem then is that the limitation is that if you have a mean field Gaussian approximation, they may actually miss some more realistic representation of the posterior. In the diffusion problem, we actually replace one latent level with many latent levels. And we fix the encoder. So that's actually fixed throughout the calculations. And I'm going to show you how we actually fix it. And then we predict only the noise added at one step, not the full image. So what we are going to look at now is something which is called a variational diffusion model. So these are the equations which I put on the whiteboard. And this is the standard Markovian hierarchical variational autoencoder. And you will see often this one shortened to this acronym here. And in this case, we have generalized the variational autoencoder to a chain of T latent spaces. And the spaces now, instead of having H, which I had on the whiteboard, I've replaced the H's with X, simply because the X's have the same dimensionality as the initial data. And here we have suppressed the possible parameters phi on Q here. And basically, this is the quantity which we have to optimize. So this is the log, the function we optimize, and then we have to calculate the gradient of that. And you see quickly that when you want to calculate the gradient of this quantity here, this is something which requires us to make some approximations. So what I wanted to discuss a little bit now on the whiteboard is actually the machinery for this diffusion or what I call them for variational diffusion models, okay? And the basic ingredients here, so the dimensionality is the same for all T's. So there is no typical bottleneck. So when you reduce the dimensionality, you typically call that for a bottleneck. And the latent degrees of freedom, they live in the same data space as the inputs. And then we are going to make a constraint. So there's a fixed Gaussian encoder. And this is the forward process. So we are going to discuss a little bit how this is implemented after the break. And we are going to have a Gaussian terminal distribution. So that means that the final one here at the final node, T, is actually going to be given by a standard normal distribution with mean value 0 and 1. And that means that the model has actually forgotten the data completely. So let's go back to the whiteboard and look at the derivation of the variational diffusion model. Any questions so far? So as I said, I'm replacing all the H's with X's because we are going to deal with the same dimensionality. So we are going to now look at a distribution, and I'm going to let, in the notation here, I'm going to let X0 go over to X. So this is the final distribution which we want. So the, let me just find my notes here. So the Markovian the variational VDM. So this is a variational diffusion model. So what we are going to do then, since the latent space is exactly equal to the data dimension, so latent space equal data dimension. There is no bottleneck, no reduction. The latent encoder is not learned. It's actually predefined as a linear Gaussian model. Is not learned. And we are going to look at why this is a model. And in the slides for this week, you will see that there are different ways of actually encoding this. And the whole recipe is based on you being able to have equations which are essentially analytically to evaluate. So is not learned, is a predefined linear Gaussian model. And we are coming back to that one. And the Gaussian parameters of the encoder, they vary over time such that the distribution of the finite latent is a standard Gaussian. So the VDM, what we call posterior, the final distribution we are aiming at, is something which we will call an x1 to t given x, the input data, and that is going to be given by some t equal 1 up to t here. And then we have the probabilities, which are given by a linear Gaussian of x of t minus 1. So that's the first step. That's the posterior for the steps from the data set till the final one. And the distribution of each latent variable in the encoder is a Gaussian centered around its previous latent one. We are going to have a specific parameterization, but before we do that, I wanted to just bring up the basic equations here. Let me just look at, where did I have it? Yeah. So these encoder distributions do not depend on a parameter phi, as we had in the variational autoencoder. Depend on phi. So in a VDM, a variational diffusion model, we only learn the conditional probabilities. So we only learn the conditional probabilities which are then given by P of theta, and this is where we will have parameters of x of t minus 1, and then x of t. So we end with x, we are given x of t, and then we use this one to sample. So the sampling procedure goes as follows. Let me set up these points before we do that. So we sample a Gaussian noise from the final probability, which we have at x of t. So this plays the same role as the prior we had in standard variational autoencoders. We iteratively run what we call the denoising. transitions, which we call P of theta of xt minus 1 of x of t for t steps. And then we obtain a new probability distribution at the very end, which is the P of x, which we want to trade. And so this is done for t times. So we have in total uppercase letter t for all the final probabilities which we want. So what we want then is the following. So we are going to do log of P of x. This is the object we want to optimize. And we can then reuse what we had previously. So we are going to have a log of P of x to t. So these are all the probabilities. So we could actually write an x0. This is the one we want to t. So these are all the probabilities. And then we integrate from some dx of 1 to t. So these probabilities, the final one which we want, which is also the P of x. Now let me change it. Let me just put x to t. So, sorry, I shouldn't have used this x0. So what we want then is that this P of for x up to t is actually given by the probabilities of P of x multiplied with a given x1 multiplied with a P of x1 given x2 and all the way up to the final one, which is this x of t. So what we have then is that this quantity can then be written out if we introduce 1 as we had before. So we have log of the expectation value with respect to these terms q from x1 to t given x, the input data, and we have the expectation value of p of x to t divided, and we are putting in 1 here. So we actually have an expectation value of the quantity of x1 to t given x. And let's set this one up before we, and this is larger equal using this Jensen's inequality of the expectation value with respect to this set of probabilities which are predetermined of log, and then I have p x of t, and this is multiplied with the probabilities from t equal 1 up to t, and then I have my p of theta of xt minus 1 given an x of t divided by the product from t equal 1 up to t here of q of x of t of x of t minus 1. So we are not there yet. So after the break, we're going to set up the 3 different terms which we end up having to evaluate. And some of this simplifies when we have fixed these values of q to a simple linear Gaussian, because then some of these expectation values can actually be evaluated analytically. But after the break, we are going to set up the different terms which we get when we rewrite this equation. And these equations then lead to the final optimization problem, for which we have to calculate the gradients. So the difference, let me just add that one, between a standard so-called Markovian variational autoencode, the diffusion model, is that we now are actually making a model for these probabilities. So we don't need to train the Q of phi's, and the latent spaces have the same dimensionality as the data space. And that leads to a simplification. So the variational diffusion model posterior, this quantity here, is actually given by a set of linear Gaussians. And that is going to simplify some of the calculations. And after the break, we are going to set up the final expression for this one. And then I will use slides more to show you how you can actually set up these terms here and evaluate them. So there are many small technicalities which are not always equally interesting to look at. Okay? The basic approach is this one. We have the log of a probability, and we want to optimize this expectation value. Okay, I went a little bit over time, but we should take a good break then, and be back at 11:20 if that is okay. So since we now have used Jensen's inequality, that means that we can now evaluate these logs, and we can actually split this in different terms. So we can isolate one term, which then links us to the probability which we are looking at, and then we will have some additional terms here. So if we now look at what we have, we can now split this final term here into 3 potential different terms. And some of these terms can actually be rephrased in terms of the Kullback-Leibler divergence. And if we have analytical expressions for some of these probabilities, this can actually be easily evaluated. Okay, so if we just keep this equation in mind, we can then show that this log or P of X is going to be larger or equal than, and now I'm going to single out 3 different terms. One is the expectation value with respect to Q of this X1 given X. So X is our initial data, which we also call X0. So we are using this distribution to generate the points X1 and X0 or X. And this is going to be given by a log of P theta. So I'm just going to isolate terms X with X1. So that's this term. So what I'm just taking, since I have the log here, I'm simply calculating the term where I pick out with the X0, which is X, and then X1. And then I can pick out the corresponding term here. Then I get 2 other terms. One, which is given in terms of the final prior for the X of uppercase letter T. So I'm going to have a Q of X of T minus 1 given X. So X, not like this, but it's going to be drawn with respect to these variables. And given X, the input variable, and I have a log of P of X of T. So this is normally fixed to a standard Gaussian with a mean value 0 and variance equal to 1. So there is no trainable parameter there. And then I have my Q of XT of XT minus 1. Like that. And then I have a new term, the final one, where I now sum up all the remaining terms of T minus 1. And then I have these expectation values of these Qs, where I'm now having a dependence on XT minus 1, XT minus 2. No, sorry, not like that. I have all the variables which I'm setting up here. So I'm just putting dots here and then given the input variable. And this contains now a log of P theta. These are trainable parameters of XT minus 1 divided by Q of XT minus 1. So these terms have different names. This first term, which we have up here, is called a reconstruction term. So we reconstruct the probability. Term. So this predicts the log probability of the original data given the first step of the latent space. This is something which you would actually have in a standard variational autoencoder, because in a standard variational autoencoder, we have only one so-called latent variable or latent variables. And the next term which we have is normally called a prior matching term, because we have a prior for the final point, x of t, uppercase letter t. And this is fixed normally to be a Gaussian. So it is a Gaussian prior. So the term which you have here is normally called a prior. So this is the guess we make on this probability at the final point xt. And as I said, this is normally given by a plain Gaussian. So this is called a prior matching term. And this term here can actually be rewritten as a Kullback-Leibler divergence, because the Kullback-Leibler divergence is actually given by this expectation value which you have here. So what it does then is that it minimizes the final latent distribution. That means this one. This is the final latent distribution, which brings us from xt minus 1 to xt using the prior. So it's going to match that one. This requires no optimization, no trainable parameters, essentially because we have a model for this one and a model for that one. So let's just mark that one. So this has no parameters. No parameters to train. Then the final term has also its own name, and it's normally called the consistency term. So it attempts to make the distribution at a given xt consistent from both the forward and the backward process. So this final term here is called the consistency term. And essentially because this piece which you see here, that is normally the forward process. So we move from the input to this x of t, and then the final x of t with uppercase letter t. And this one is then the reverse process or backward process. So what this is doing then is that it attempts to make the distribution of xt consistent for both forward and backward. And there is, as you will see later, denoising step from a noisier image, which matches the corresponding noising step from a cleaner image at every intermediate step. And it's minimized when this is tried. So this is minimized, this function here, when it's trying to match this Gaussian distribution. So these guys, which you see here, these will always, in the standard way these are being set up, this is going to be given by a Gaussian distribution. So we are not actually fully there, but these are the expressions to which we have to take the derivative of with respect to the unknown parameter theta. And even though we have analytical expressions for this one and for that one, since you typically have something like T100 or more steps, this is going to be time intensive in the training. So what I want to do is to bring up some elements from the slides where you have additional wordings. So if we now switch from the whiteboard to the slides for this week, so let's just do that. So there is a file which I call addition to week 15. And this is the one which I wanted to use a little bit now before we go back to the week 15 slides. which then contain details on how you can calculate the Qs, these probabilities. So what we went through is actually this variational diffusion models. And what we are going to see then, so let me just find the right one. So these were the equation we went through. So there's a reconstruction term. It predicts the log probability, as I said. And then we have the prior matching term. And it has effectively no parameters, no trainable parameters. It requires no optimization. And then we have the final consistency term, which is also given by a Kullback-Leibler divergence. So the setup which you would typically see here is that you have a step one, you pass the real examples, and this goes through all all these different steps, and then it generates a fake example and pass it to the next step, and then train, and then you train a generator, which is then regenerating the final probability distribution. And this is actually taken from this article which I mentioned from Luo. So the cost which you have to consider in this training is actually the consistency term. And the consistency term, and you can really see that, is actually this term here, because that is the one now which depends on all the steps you make. So if you have 100 or more steps, this clearly becomes the time-consuming element in the training of a diffusion model. So all three terms have to be computed as expectations, and they are typically approximated with Monte Carlo sampling. The issue then is the consistency term, which is actually an expectation over two random variables, and for every time step. So potentially that means a high Monte Carlo variance. And summing all these different consistency terms, let me just quickly remind you of the consistency term, which is this one. That can also lead to high variance when you have a large value of the number of steps. So it's normally pretty efficient, simple. It can generate highly realistic images, and it excels at closely matching the distribution of real out images. So for GANs, which we're going to discuss a little bit later, this can actually really outperform the quality you get when you train a adversarial network. So the input types, which are typically used in these diffusion models, text to image, layout to image generation, many other types of generative tasks. So the denoising, diffusion probabilistic models, actually you have a probabilistically remove noise from data, and during training learn how noise is added and how to reverse it. And the outputs are not just noise-free, they closely resemble the original data. So this reverse diffusion, which we discussed in particular with a consistency term, is normally slow. So if you have up to 1,000 steps, there is actually, and this is done 6 years ago, according to Song et al., generating 50,000 small images takes something like 20 hours on an NVIDIA. This is an old graphic cards. Whereas some of the other methods, and if you use a variational autoencoder, if you take the codes which we have for this week, you will see that the variational autoencoder, which I have encoded there for the MNIST data set, takes just less than a minute. Whereas my diffusion model, which tries to do the same thing, is actually going to take hours, unfortunately. So these kind of models here, you have denoising diffusion implicit models, which actually stand out for its efficiency and quality. So what I wanted to say a little bit about now is how do we actually encode this probability Q? So I'm going back to the weekly slides for this week.
What we're saying is basically when it comes to optimization,
yeah.
The GAN is,
yeah.
is it's more cost efficient, you could say, but,
exactly.
But the diffusion model basically outperforms if you have the resources.
Yeah, exactly. And it gives you very high quality images. And that's why these diffusion models are actually those which are being used in many of these softwares like DALL-E, etc., etc. but it takes more time to train.
Enough time.
Exactly. Actually, this is one of the things we discussed in the very beginning, because many of these algorithms are available to everybody, and you can start implementing them. But if you don't have access to resources, then we spend. I think I mentioned this some time ago. So when we have research applications, we typically have to include the estimated cost for computational resources, and you pay 5 Norwegian kroner per GPU hour on the national resources. And the type of calculation I've been running, which is essentially solving quantum mechanical many-body problems, that's my cup of tea. We had something like 100,000 GPU hours, which is 500,000 Norwegian kroner. So the bottleneck, if we are thinking of that, is access to compute power. And that's why I really recommend, since many of you will actually face that problem, is to at least use the University of Oslo machine learning nodes. So just search for UIO ML nodes. And I guess everybody here has basically done that, been using them. This is highly recommended. Because else you're just gonna be stuck with your code running for hours and hours. Unless you have a laptop or access locally to a very efficient PC with the GPUs. Yeah, it's a sad case actually. We know how to do things, but we cannot do the interesting things because the interesting things require a lot of training. Okay, so I wanted to go back now to the slides for this week, and I'm going to say a little bit about the type of training which we and how we can do that, and how we can set up this encoder part. So the encoder part, there are many ways of doing that, but as I said, it's normally given by a fixed Gaussian encoder, and there is a linear dependence between the previous step and the new step, which is given by this parameter alpha t, and this alpha t then is given by some 1 minus beta t, where this beta t is actually given by a design choice. So nothing here is trained. And this alpha t then is designed so that when you reach the final point here, this is close to a normal distribution. So that means that when t goes to uppercase letter t, the model forgets the data completely. And you will see that in the calculations, if we get time at the end, you will see then that you just end up with a totally blurred picture. So here comes the type of machinery which is typically involved. And I said there is no training. And what I did put in the slides here is actually some of the steps which are needed. So keep in mind then that this x, which we have, x of t, they have the same dimensionality as the data set which we have. And there is a linear dependence. And the way you set it up, so you actually write one step as x of t, the square root of alpha, x of t minus 1, plus some added noise. And the noise is just given by a plain Gaussian distribution. And then you have the unrolling of the two steps. So you can actually rewrite this x of t, and this is just basically plain linear algebra. And you can actually set this up in terms of xt minus 1, xt minus 2. And when you do that one, you have a dependence given by xt minus 2. And since you have this relation here. Then, when you look at the closed form marginal distribution, this x of t starting with x0, then you would have a definition of this alpha bars, which is just a product of these. So you can continue this induction here, and that means that you get a closed form marginal with a given x of t starting with x0, which is your initial one, where you can then simply set this up as a normal distribution, and where you have a recipe for setting up the different points. So this is normally called the signal coefficient, decays towards 0. This is called the noise coefficient, and it grows towards 1. It's pretty, when you look at the equations, you can see that. And at t equals 0, this x is actually equal to the original data set. And then at t equal uppercase letter t, from this equation, you will then see that this x of t is just pure noise. So this is your, in a sense, there's no forward pass for a network which is needed. This is just basic arithmetics. So that makes it easier to perform this training. And then there are different ways to do the scheduling here. And you can have a linear schedule like this one. You can have a cosine schedule. So there's a lot of alternatives. And again, if you go into the literature, you will find this kind of more, what I would like to call more ad hoc rules for setting up this kind of signal to noise ratios. And different practitioners have their own approaches to this. So this reminds you a little bit of what we had when you look at Adams as an optimizer, root mean square propagation, etc., etc. So the whole thing now is that you want to have a tractable forward posterior. So in a certain sense, this reverse is actually intractable. But when you condition on x0, it is tractable via Bayes' rule. And this is the quantity which is being used then to actually set these up. So you have the probabilities of xt minus 1 given xt and x0. And then you use Bayes' rule, and then you can set up the equations. And with the last equality here, then that uses what's called the Markov property. So where you simply have then this one given by xt with xt minus 1. And each factor here, which you have in this equation, is a Gaussian. And if you substitute and complete the square in xt minus 1, then that yields a Gaussian in xt minus 1. So these are some of the kind of, I added these kind of equations here so you have a more complete recipe in case you want to encode this yourself. The codes which you see online, they follow this, basically this recipe. And these are just intermediate calculations here, just plain algebra. So it's not very exciting. I'm not going through this on the whiteboard because I would put you guys to sleep. And this is just some intermediate steps which I encourage you to take a look at. And then we have the mean value, which we need to evaluate. And this mean value is read off from the linear term. And you can set that one up again by multiplying with this beta of t. And then you have an expression for the mean value. And then you have a forward posterior, which is an exact result, which is then given in terms of mean value, which is set up here. And then this term beta and the value xt minus 1. And then you have explicit expressions for evaluating these. And this is a target the learned reverse process must match, because this becomes a probability. If you look at this one, if you go into the consistency term, if we just remind ourselves of that one, the consistency term has actually a part where we take the ratio between the backward probability divided with the forward process. And if we now look at that, we have, if we substitute this structure into this standard result, the Markovian variational autoencoder, this is the reconstruction term we have to set up. We have the prior matching, which is simply given by non-trainable parameters. And then we have these denoising matching terms. And if I have this LT equals 0, that ensures simply that this is given by normal distributions. So there are some additional things. So why the condition on x0 reduces variance? So the first attempt uses normally this term in the Kullback-Leibler divergence, which requires an expectation over 2 random variables per term. So this is heavy. And this has normally a high Monte Carlo variance. The second attempt actually uses this probability, and then you can actually show that this is given by this Kullback-Leibler divergence. And that conditions form is a tighter bound and requires sampling only x of t proportional with x of t given x0, which is one shot via the closed form marginal. So there's only a single Monte Carlo draw. So there are lots of these kind of practicalities, practical elements, which enter the setup of a diffusion model. Yeah, there's another thing. When you have a Gaussian, there is actually a closed form evaluation, which makes also life a little bit simpler. So for general Gaussians, if you have two Gaussians and you're looking at the Kullback-Leibler divergence, which we also discussed last week, then this is something which has an analytical expression. And in our case, both distributions have the same variance. So this log, which you see here, and the traces, they actually cancel each other exactly. And then you're simply left with a term, which is actually pretty easy to evaluate. So training reduces to matching means, and the network only needs to predict these mean values. So these are some other technicalities when you have a fixed probability distribution. But you see again that the fixed probability distribution makes things a little bit less flexible. Because if you have more complex data, which are eventually not represented by Gaussian, then you may have to actually work a little bit harder. So I'm going to skip these slides here. These slides are more just for the completeness. And there are observations which can be useful to implement. But in essence, when you're going to implement it, the most important thing, and the reason why I mention these elements, is not because we are going to force you guys to write your own diffusion model, because that would definitely be a full semester project. But you have to understand the basic inputs to the model and how things are actually done. And then we would just use ready-made functions for diffusion models. So in this case, I mean, you will see that many of the practitioners have, for instance, dropped the time-dependent weighting, and the average uniformly over T gives a simple objective with better sample quality. These are all kinds of ad hoc ways of implementing it based on observations from calculations. Yeah, I'm going to skip this one as well. And some of these are basically technicalities which are not that interesting. I wanted to basically just leave this as a background material. I wrote to you that the slides contain much more material than needed, but I have filled in details which you can look up if you are interested in the practical implementations of these diffusion models. So diffusion models are typically extremely popular. And when you make a final analysis, it's important to actually compare with other methods like variational autoencoders, GANs, Boltzmann machines, etc. So if you look at the two methods which we have been discussing now, the variational autoencoders and diffusion models, so both maximize a log of P of X, which essentially is given by this expectation value minus this Kullback-Leibler divergence, except that when we deal with diffusion models, this second term depends on all the intermediate steps as well. So this term is common for both. And this term here simplifies for the variational autoencoder because we have only one latent level. So just to remind you of that, if you look at this term, if we go back a little bit and skip all this crap here. So the variational autoencoder has this term, it has this term, but not these. So the Kullback-Leibler divergence for the diffusion model has to include all the other steps. And that complicates things. And this is where we have this, what we call the denoising matching terms. So for the variational autoencoders, we have only this prior matching term. And the typical, when we do this kind of diffusion models, we often end up with more than 100 steps. And you see that that can quickly really grow your computational time. So in a variational autoencoder, we also learn this Q of 5. So that becomes a parameter, whereas here, the encoder part is actually fixed. And that makes often that encoder part easier, even if you have many steps. The bottleneck is the same as you reducing the dimensionality, so that looks like a bottleneck, which means that the latent space in a variational autoencoder is normally much smaller than the dimension of the original space. In the diffusion models, it's the same dimensionalities. So here we have X from the latent space, whereas here we actually denoise, we actually put in a lot of noise, and then we reconstruct everything from a fully noisy picture here. We have only one Kullback-Leibler term for the variational autoencoders, whereas we have T-1 for diffusion models. And that is where we have the heavy evaluation here. And typically we have one decoder call, and here we have a T denoiser calls. So the diffusion models is typically equal to a variational autoencoder with T latent levels, fixed encoder, and no bottleneck. So the pros and cons of these methods. The variational autoencoder, when you run the codes which you have for week 15, is typically pretty fast. It's compact structure latent space, and we will see that in the codes. When we look at the latent space for the MNIST data, you can essentially reproduce all the data sets with only 2 degrees of freedom for the encoder, for the latent space. So it's a stable training, and you also have a closed form for the Kullback-Leibler divergence. It's pretty good for clustering, also interpolation, and it scales well to large data sets. You often get more blurry images. And there's also the risk of the posterior that can collapse in the training. You have to train this estimated lower bound in the optimization. And there's a mean field limits, which can actually, the mean field which can limit the posterior quality. On diffusion models, on the other hand, this is the state-of-art models. It's stable training. It's grounded via this estimated lower bound plus score matching. It's pretty flexible, but it's very slow, extremely slow. There is no compact latent space, and it has a high memory usage for large T's. And it's less natural for representation learning. So these are some of the pros and cons of these methods. Here you have the equations. When we look at the complete things we have to encode. So we have the forward step. So this is a normal distribution. We have the forward marginal, which is this one, which is actually the quantity we want at the end, because we want the link to from x0 initial one to an xt. We have the sample, which is given by this one plus some noise. We have the forward posterior mean. We have the forward posterior variance. And then we have this noise parameter mean value, the training loss, which is typically just the difference here, which is a mean squared error. You have a score function. The reverse step, you can actually set up xt-1. And then you have different ways to parameterize these alphas. Yeah, just I put up lots of references here if you want to read more. The thing I wanted to say a little bit about is just to start scratching the surface of GANs and adversarial training. And we will continue with this topic in the last lecture. So if we look at the big difference between, and we could have added here Boltzmann machines. So Boltzmann machines, variational autoencoders, and diffusion models, is that we actually obtain a probability distribution. We have an explicit training, which gives us a final probability distribution, which we then can use to make, let's say, new images. Now, a GAN, on the other hand, is based on game theoretic ideas, and it's an adversarial game, and there is no likelihood which is produced. So it never evaluates the same function which it never evaluates this log of the probability which we want to optimize. If we have minus log, we have a minimization problem. Plus log is a maximization problem. And it contains two elements. Actually, the whole idea is extremely simple, and it's very neat. So Goodfellow was the person who introduced that back in 2014. So if you're interested in a probability distribution, this is probably not the method you would choose. It contains a discriminator which provides the training signal by classifying real versus fake data. And it has a generator which actually tries to cheat the discriminator by producing fake data. So it's the competition between the two, which then reaches a balance here. And there is no likelihood computation. So there's a cost here, there's no likelihood. It can be unstable, that's another thing. It can actually give pretty sharp samples. But if you're interested in a probability distribution, this is not the method. So it contains, and also if you go into the textbook by Goodfellow and company, you will then find a description of the generative adversarial networks. And it pits two neural networks against each other in a zero-sum game. So you have a generator which often starts with just some noisy data. And then it gives a synthetic sample, which is given by this noisy data, which you plug in. And then it tries to fool a discriminator and implicitly defines a distribution P of G. This has the input image, for instance. It could be an image you want to train on. And then it gives an output where X is the real image. And the goal is actually to distinguish real from fake. Neither network sees the other parameters. They improve each other through adversarial feedback alone. So there's a kind of architecture you could think of. So you have the real data, which is fed into the discriminator. You have some noise, which is fed into this generator. And so this typically maps noise to some data space. So data space is then defined by the input data. And then it has D, which maps this into some probabilities here, from the image to some probabilities. So the training alternates. You freeze G and update D, freeze D and update G, back and forth. So there are, GANs can actually be used to all the types of training which you may be interested in. So you can have unsupervised training, which is often the case you are interested in because labeled data is expensive. And often there's a human who has labeled the data for you, which means that you also have less data in the training. Whereas in many cases, you have data which you don't know exactly what it is. And so that means that you have unsupervised learning, but you can also have a kind of semi-supervised type of environment. The most common ones are unsupervised and supervised. And then the applications are actually quite many. So image synthesis, text-to-image translation, video prediction, et cetera, et cetera. Now, it's actually been used in, I know that some of you are doing particle physics, and you probably encountered the usage of GANs in particle physics experiments in scientific simulations. So what I thought of doing now is that we could stop here, because I wanted to use the last lecture to discuss a little bit more about GANs, but I wanted to give you a kind of basic motivation for what is coming. And the last lecture is going to be the one not next week, because that's a public holiday, but the week thereafter. And then we will also do a summary. So I'd suggest we stop here. And the last lecture will focus at least the first hour on generative adversarial networks. So that means that the slides which you see here are also slides which we will discuss the last week. And then we will have a summary and discussions of the project for that last day. So you will see this material again in roughly 2 weeks from now. Okay, I'm going to stop here because we have reached the hour. So let me just stop the recording.